Yep,
Yeah,
just hit
great.
record.
Yeah, good morning, everybody. I have really been looking forward to this seminar this morning. Ever since, to be honest with you, I heard Dr. John Abraham uh, talk a little bit on the PBS NewsHour a couple of months ago about what he's going to be talking about this morning. Um, Dr. John Abraham is a climate researcher at the University of St. Thomas. His team studies ocean warming and the rate at which our planet is warming. He also researches extreme weather, sea level rise, and the social costs of climate change. The recent global data that shows this sharp increase in the temperatures of our oceans, it's even more frightening and more compelling evidence of this really rapidly warming climate. And this morning, John is going to share the latest knowledge about climate change, focusing on both global and regional factors. And he's also going to discuss pathways forward to reducing our impact in the future. So, in addition to being a faculty member at the University of St. Thomas, John is co founder of a startup company that provides drinking water to the developing world. He has published some 400 pieces of scientific research, and he has about 25 patents. John, thanks for agreeing to give us a talk this morning, and really looking forward to your talk. Take it away. The floor is
It's a
yours.
pleasure. Yeah, it's a pleasure. If you can't hear me, just let me know and I'll try to adjust things on my end. But it's a pleasure to talk to you. Your group, the MPCA, does excellent work around the state, and it's an honor to contribute to developing some knowledge and some capacity on climate change. So it was a great lead in, very humbling, makes me a little blush with embarrassment. Um, just to tell people really briefly, my team studies climate change, and in particular, how fast is the Earth warming and how far is it going to warm into the future. And in addition to that, we study impacts, social impacts. And you might wonder, well, so I have a mechanical engineering background. You might wonder, why is a mechanical engineering working on climate change? Why aren't they fixing cars? The answer is mechanical engineering covers the subject thermal sciences, which is heat and fluid flow. And climate change is heat and fluid flow. We've got oceans and we've got the atmosphere. Those are both fluids, and clearly heat is related to global warming. So it turns out my niche in mechanical engineering matched up with climate science very closely. So I'm going to go through these some slides. It's not going to be too in depth, but it'll be pretty balanced, I hope. And I'm appreciating any questions that people have. So maybe we can have a discussion after the fact. But I want to start out with, what do scientists know? There's a lot of talk about climate change. Is it happening? Is it bad? Is it this? Is it that? But let's talk about the facts. These are the things that are in evidence. Warming is unequivocal. There's no one who's debating climate change anymore, or at least whether it's happening. Very few people are debating whether it's happening. The evidence is clearly showing climate change is occurring. The measurements are unequivocal, and it doesn't matter who's taking the measurements, where they're taking the measurements. Everywhere is warming. Each of the last 5 decades is warmer than the prior decades, but warmer now than it's been in well over 1,000 years. This is something most of particular interest to your group. Extreme weather events are increasing. So those include heat waves, droughts, rainfalls, and floods and hurricanes. We'll talk about that more later. We're losing ice on the two great ice sheets on the planet. That's Greenland and Antarctica. I'm going to talk about the implications of that. We have decreased snow cover, which is something we know about in Minnesota. If you enjoy winter outings, you know that we've got a lot less snow cover. Sea levels are rising. The poles, North and South Pole, are warming very fast. We're losing glacier ice, and the oceans are becoming more acidic. Wow, this is just so depressing when you look at these things. Fortunately, I will transition to a message of optimism, but these are undisputable facts that we've observed. Now, about 90% of climate scientists look at these things and say they're all connected. All of these things are related to a common cause. There's a tiny minority of holdouts on the scientific community that gets smaller every year that say they're not connected. but we know in the general public, there are still a significant number of people that don't recognize these things are related to each other. So why do we know humans are causing the climate change? Well, it's not just that the Earth is warming, it's warming in the right way. And we call that fingerprints. So here are some fingerprints of human climate change. And I want to focus your attention right here, cooling of the upper atmosphere. Okay. Some people will say, hey, John, the Earth is warming because the sun is getting hotter. Okay. That's a testable hypothesis. If it was the sun that was getting hotter, we would expect the entire atmosphere from top to bottom to get warm. But we're not observing that. We're observing the lower part of the atmosphere is warming up, but the top is getting colder. And that's because global warming gases hold heat down. It's like putting an extra blanket on at night. It holds heat into near your body. And climate change is working the same way. So cooling of the upper atmosphere is actually a fingerprint that greenhouse gases are causing the warming. Another fingerprint that I want to point out is nights are warming faster than days. Again, if it was the sun that was getting hotter, you would expect days to warm faster than nights. We're observing the opposite, and that's because greenhouse gases have their biggest effect at night. The last one I want to point out is in the lower left. It's winters warming faster than summers. Again, if it was the sun, we would observe the opposite. But we're observing winters are warming faster than summer because greenhouse gases have their biggest impact when the sun's not shining. So the point I'm trying to make here is it's not just that the Earth is warming that makes scientists so convinced that humans are the cause. It's that it's warming in the right way or with fingerprints of human intervention. So this is one of the most famous graphs in all of science. It's called the Keeling curve, named after a guy named Charles David Keeling, whose citation is in the bottom of the screen. And Charles David Keeling started measuring CO2 in the atmosphere. And he started his measurements in 1958. And he is no longer around, but his son is continuing those measurements. And here is the record over the past 65 years or so of greenhouse gases in the atmosphere. Now, the first thing I want you to notice is they're going up. There is a significant increase from 1960 to now, and we're well over 400 parts per million, ppm, which is the units on the left. The second thing I want you to notice is that it's in a sawtooth pattern. So greenhouse gases go up and down, up and down, up and down, but every year they get higher. The reason why it's a sawtooth is because in the spring, plants grow and they suck the atmosphere out of the sky. I'm sorry, they don't suck the atmosphere. They suck carbon dioxide out of the sky. And in the fall, plants decay, their leaves fall to the ground, they decay, and that allows the carbon from the leaves to be released. So there's an annual cycle, an up-down cycle every year, but each year it gets a little bit higher. And we are most concerned about the long-term trend. Now, I know some of you are thinking, well, wait a second, John, there is a springtime in both the northern and southern hemispheres. And there's a fall in the northern and southern hemispheres that are at different times of the year. That's true, but it turns out almost all land is north of the equator. So what you're seeing, this sawtooth, is really due to plant growth north of the equator. Carbon dioxide is not the only greenhouse gas that we've focused on. Two other important greenhouse gases are methane and nitrous oxide. And this plot shows the long-term concentrations of carbon dioxide, methane, and nitrous oxide back for about 2,000 years. And what I want you to notice is they were more or less stable for about 1,700 years. And then at the onset of the Industrial Revolution, all those greenhouse gases started to rise. So it's not just carbon dioxide. There are other greenhouse gases as well. It turns out carbon dioxide is the most important human-emitted greenhouse gas. And that's why it gets so much attention, but the others are important as well. Okay, so who cares if greenhouse gases are warming? I mean, if there's no impact, we don't care, right? Well, let's look at the impact. I'm showing you a graph of global mean temperatures. Now, this is just Earth average temperatures. And you see a lot of black dots. Those black dots represent the temperature, what's called the anomaly, or a temperature variation in any given year. And you'll notice that some black dots are high, some are low, some are then high again, low again. So there's a lot of what's called noise. Let's focus on the long-term trend. The long-term trend is shown by the red line, and that trend shows unequivocal warming since approximately 1960, maybe even back to about 1910. I'm going to list out for you the, I believe, 12 hottest years ever recorded by humans using thermometers. 2023 broke the records, hottest year on record. By the way, it's sort of a coin flip as to whether 2014 breaks a new record. It's going to be really, really close. But number one is 2023. And then here are the other years. And again, these are the hottest years ever recorded by humans on planet Earth. And if you think about it, what is the chance this would, what is the likelihood this would just happen by chance? Let's go a few more. Maybe I have 16 of them. 16 hottest years ever are in the 2000s. By the way, this data is from NASA. And if you want to go get the NASA data, all you have to do is type this GIST temp in the lower right. And I do try to provide links or references of the data so that people can find the data for themselves. All right, so I want to show you some of the outcomes of some of the research that my team has been working on. And I work with folks from Asia, Europe, and South America. And we study ocean warming. And some of our research has picked up a lot of media attention because we've been struggling to come up with analogies to explain how much warming is happening. And this is a CNN article about our research in 2020. And the amount of warming in the year 2020 was equal to 5 Hiroshima bombs of energy detonated in the oceans every second of every day of every week of every month for the entire year. 5 Hiroshima bombs going up every second. It's a staggering amount of heat. But that analogy helps drive the magnitude of the problem home. Our work has also been picked up by other news sources like the Telegraph in England, even Fox News covered our research, and Newsweek and so forth. So this is research that's coming right out of Minnesota. This is front of the line, breaking edge research, and we should be proud that we have an infrastructure set up in our state to do this kind of research. This is a graph that we provided to Minnesota Public Radio. You may know Paul Huttner, who runs ClimateCast there. And this is data from my research team. And it shows the heating of the oceans back to about 1960. And you can see that the rate of the heating goes up. I mean, it's a clear and unequivocal trend upwards since approximately, I've got to move this little thing, since approximately 1985 or so. And you might be wondering, well, why is part of it blue? Why is part of it red? Because when you talk about temperature changes, you always need to set a baseline. It's and we set our baseline to the horizontal line that goes across the screen. So basically, anything above that baseline, we colored red. Anything below the baseline, we colored blue. But the colors don't matter. All that matters is whether that those bars are going upwards. And by the way, you can see a note above the table called IAP data. That's the research team I'm working with, Institute of Atmospheric Physics out of China. And they're one of the groups that measures ocean temperatures. All right. So let's go back a little bit further. I want to go back further in time, and this is a graph. And my wife always tells me that every time you put a graph on the screen, half the people fall asleep. Now, I know that's not true for MPCA because you guys are data wonks, just like I am. But this is, I think, one of the last graphs I've got. This is a graph that goes back 400,000 years on the left-hand side. And you can see this KYBP, that stands for kilo years or 1,000 years before present. And on this graph, you see two colors, green and red. The red is temperature. And the green is the amount of greenhouse gases that were in the atmosphere. And what I want you to first notice is that the two go together. When greenhouse gases go up, temperature goes up. When greenhouse gases go down, temperatures go down. When temperatures go up, greenhouse gases go up. When temperatures go down, greenhouse gases go down. We call those handcuffed. When one moves, the other moves. And this data shows how tightly connected the Earth's temperature and greenhouse gases are. For the last 400 plus thousand years, they've been handcuffed together. So we should expect they continue to be connected. Some people, the doubters of climate change, are saying, well, greenhouse gases might go up, but that doesn't mean temperature is going to go up. And this is data that 400,000 years of data that flies in the face of that. I think I took a slide out, but I wanted to explain how do we get data back 400,000 years? I mean, we didn't have scientists running around the planet with temperature sensors. The answer is we use what are called proxies. Those are signals from nature. I'll give you an example of a proxy. Let's say that you go camping in northern Minnesota in the Boundary Waters, and while everyone else is sitting around a campfire having s'mores and drinking hot cocoa, you decide to go into the woods with a shovel and you start digging. And let's say you dig down into the ground and you discover crocodile fossils and palm frond fossils. You would conclude that the weather probably was warmer in the past in Minnesota. It's a signal from nature about temperature. Some other signals from nature are the pollen. We can go into the ground or lake sediments and find what kind of plants were growing. Were they warm weather plants or cold weather plants? We look at ice cores. We can look at what are called stalactites and stalagmites. I think that's called paleo. I don't know, some crazy word. We can also look at tree rings. Trees grow more on warm, wet years than on cold, dry years. So there's a bunch of different signals that we can use to go back this far. Now, the graph you're looking at is from what's called Vostok, which is an ice core in Antarctica. And the way this graph was made is a long ice core, probably about 2 miles long and about this big in diameter, was drilled. And when that ice core is pulled out of the ice, it has layers in it, a lot like the rings on a tree. And using those layers, you can count back in time. In addition, the isotope of oxygen that's in the ice tells you what the temperature on the planet was at the time. So we get time and temperature. And thirdly, the ice has dissolved atmosphere in it, little bubbles of atmosphere. So when you take the ice core to a lab and you melt it, the ancient atmosphere goes into your lab and you can detect what greenhouse gases were in that atmosphere. So with ice cores, you can get time, temperature, and greenhouse gases. And that's exactly how you make a graph like the one you see on your screen. All right, so let's look forward. I mean, we've looked at the past and we've looked at greenhouse gases, they're increasing. We've looked at the past temperatures. What's going to happen in the future? This is a graph that shows temperatures over approximately the last 1,000 years. And the red stuff is what we've actually measured with thermometers. And by the year 2000, we were already concerned about the temperature rise. That's the end of the century. And just so you guys know, we have hit, we're about right where my cursor is right now. We're about a degree, almost a degree and a half over pre-industrial times. So this temperature is rising rapidly and we're seeing it in our measurements. And it makes you wonder, like, what kind of world is this going to be? It's going to be a very different planet. And if you wonder, well, John, you're talking about 2 degree, 4 degree, or 6 degrees Celsius increases. Who cares about that? I mean, in an average day in Minnesota, the temperature variation is much bigger than that anyways. Well, when you look at temperatures averaged over the entire year and over the entire planet, just a couple degrees makes a huge impact. To go from having ice sheets in Minnesota year round to our current climate, that's about a 5 degrees Celsius change. So 2, 4, or 6 degrees Celsius is a major, major, major earth-shaking and earth-shaping temperature change. Let's look at some of the impacts in the U.S. So this is a image from the U.S. Drought Monitor Project. You can actually, if you're at your computers, you can Google U.S. Drought Monitor and you can get a map of what it looks like now. And this is a map of August 2022. And I just picked this because it was a recent drought that hit the southern and western part of the US, and it's color coded. So you can see where the drought is extreme versus exceptional versus severe. We are experiencing more and more severe and long lasting droughts in the US than we should, and it's because of climate change. And think about the impact that this has. I mean, California had the worst drought that they've ever had in 1,200 years. And this was just a couple years ago. And it caused $4 billion in lost agricultural productivity. So that affects us all. We're not just talking about polar bears, and we're not just talking about ice sheets. We're also talking about the economic underpinning of our society. There was a severe drought in the Midwest in 2012 that cost $35 billion. So if you are a fiscal conservative, the implications of climate change should scare you. In addition to drought, we're having more extreme weather. Now, this is a map of the US that shows the 99th percentile precipitation. What the heck does that mean? It turns out when you have a storm, the storms you really worry about are the most powerful ones. Like if you have 10 1-inch rainfalls, that's not going to cause damage. But if you have one 10-inch rainfall, that's going to cause a lot of damage. So it's the most severe storms that matter. And what this map shows is the top 1% storms. So the biggest of the big storms. How are they changing over time? And if you're in the northeast part of the US, they've increased 55%. If you're in the central part of the US, where Minnesota is, it's 42%. And in fact, it's an increase everywhere across the country. Why is this important? Because intense precipitation leads to droughts, and it leads to floods, and floods are major economic costs of climate change. So, I've shown some data about droughts and I've shown some other data about floods, and those two things can be at odds with each other. So as we heat up the planet, we put more moisture into the atmosphere. And we know that in Minnesota. Listen, it is more humid in July than it is in January. And that's because warm air holds more moisture. So warmer air gives you more intense rainfalls. But warmer air also increases evaporation. So, and that leads to drought. So what is happening is we are having bigger swings. We go from drought to flood to drought to flood much more vigorously and violently than we did in the past. The general rule of thumb is that if you're in an area that is currently wet, you are going to become wetter with climate change. So that's like the northeast part of the US, northeast and southeast. If you're in an area that's currently dry, you're going to become drier overall, and that's the southwest US. And if you're in an area that's sort of in between, you're not going to become wetter or drier, but you're going to see bigger swings from wet to dry to wet to dry, and that's Minnesota. So Minnesota, we can experience warming climate with more extreme swings of weather. All right, I'm going to shift a little bit to other weather patterns. This is a map of what's called SST, which is sea surface temperature anomalies. And anything that is in yellow or red is warmer than the long-term average. Anything in blue is colder than the long-term average. And why would I have picked October 8th, 2018? What was happening October 8th, 2018? Let's find out. This was happening. A big old hurricane was barreling into the panhandle of Florida and Louisiana and Alabama. And I'm showing you a satellite photo. And it's a satellite photo that's been stitched together. On the right-hand side is a city before the hurricane hit. And on the left-hand side is the stitched photo, the adjacent photo of this same location after the hurricane hit. Now, why do we care about sea surface temperature? Why did I bring that in? Because it's sea surface temperature that weather. Water temperatures give fuel to hurricanes. They make them bigger, stronger, wetter, bigger storm surges as they give fuel to other types of storms. So the oceans are really, really important. They cover 70% of our planet and they drive weather. So as we get warmer oceans, we're going to see more of this kind of damage. All right. This is US billion-dollar disasters adjusted for inflation from 1980 to 2023. This is in billions, not in millions. Last year, we had $600 billion. I mean, this is a jaw-dropping graph. The increase of costs has been really remarkable. And for people who think climate change is not a clear and present danger, or it's just polar bears and endangered species in the poles, this is proof positive that it's affecting us in the US and in Minnesota. And we know that our economies are connected. So if we get a big storm in Florida that the government has to fund repair efforts, well, we pay for that, even though it's not in Minnesota. So costs to other parts of the U.S. also affect us, as you guys all know. And you think about it. I mean, $600 last year. What would happen if we spent $600 billion on climate? I mean, we would be in a different world. And the old adage, penny wise, pound foolish. That has been the U.S. Over the last 20 or 30 years or so. I'm going to shift some attention to ice, and this is a photograph of what's called a moulin, which is a fancy French word that is fun to say in the morning. And on the right-hand side of my screen, you can see a river of water on an ice sheet, and there's some people in the background. That river of water is called a moulin, and it's flowing toward the camera holder. And right at the center bottom of the image, it is falling vertically downwards into a crevice where it goes to the bottom of the ice sheet. Why do we care about that? Because these moulins are melting ice, and the water flows to the bottom of the ice sheet. They get between the ice sheet and the ground, and they lubricate that connection and help speed ice loss. So moulins are contributing to rapid ice loss. I think this image is on Greenland. By the way, there was an article out just this week about the so-called Doomsday Glacier in Antarctica, which is melting from below because warm ocean waters is hitting underneath it. So melting ice is an enormous issue that we've got to deal with. What you see on your screen now is a lake. There's a motorboat, and in the background is an ice sheet. And this is a lake on top of Greenland. Let's shift our attention to the South Pole. This is an image of Antarctica. And Antarctica has two parts, the east and the west. The east is on the right-hand side of the screen. It's huge and generally stable. The west side is smaller but unstable because the ice in the west side is pinned atop mountains, whereas on the east side, it's actually resting on land. But I want to draw your attention to the Larsen B ice shelf that is highlighted in red. And then I'm going to show you a series of satellite images. This was January 31st, and I want you to see these little black dots. Those are moulins. And over the period of a month and a half, the entire ice sheet collapsed, ice shelf collapsed and flowed into the water. For perspective, it's the size of Rhode Island. And that this ice sheet has been around, ice shelf had been around for well over 10,000 years. This shocked scientists. In fact, it was one of the inspirations for the movie The Day After Tomorrow. I think that's what the movie was called. Here's a satellite image of another ice shelf. They're called the Wilkins Ice Shelf that broke apart in the 2009s. And I don't know why I'm shifting gears here. I'm going to now show some flooding. This is sort of a disjointed talk. I guess we're back to extreme weather. This is Sacramento, January last year. after torrential rainstorms. And remember how I said California was going through this terrible drought, worst drought in 1,200 years? And then it got this inundation with heavy precipitation and flooded. And that's typical of what we see with climate change. We're going from one extreme to the other. But that's Sacramento. Think about the economic costs of that. Here's another photograph from California. Again, flooding from rainfall. And this is Minneapolis, St. Paul. I think this photo is from St. Paul in 2019. This next one is Minneapolis 2019. This is after a rainstorm. Are you kidding me? A place where I used to buy beer when I was in high school, Hum's Liquor in Uptown, flooded. And someone's walking around with, I hope, very tall waterproof boots. The flooding and negative weather consequences are not just happening in the U.S. This is in Kenya. By the way, Kenya just had major flooding in Nairobi this year that actually wiped away part of a large ghetto. So I know that this image is from 2020, but we've got other images that are more recent. You've probably heard about the Australian drought and fires that swept their country. No country has been spared. England has had major flooding. We've had Lake Mead. Parts of Lake Mead are drying up. Lake Mead's in a little bit of trouble. And then we've got glacier loss. So this is a series of two photographs. The top photograph is from 1899, and this is what's called the Reed Glacier. And the bottom photograph was 20 years ago. So things have progressed worse in the last 20 years, but this is 2004. And the camera is in the same location. The camera is in the same location. So I can see the same mountains are in both photographs. And you can see how far the Reed Glacier has retreated. It's all the way here on the right-hand side in the lower image. Here, the next slide shows the McCarty Glacier. The bottom is 1909 and the top is 2004. Again, huge retreat in glaciers. We've got the Muir and Riggs glaciers. This is a 60-year decline in that glacier. And we're also losing other ice. We're losing glaciers in Antarctica. This is an interesting one. This is 2020. And on the left hand, this is a small island off of Antarctica. On the left-hand side is the island with pristine white snow cover on February 4th. And then just 9 days later, a bunch of that ice had melted and huge melt ponds had formed. Temperatures got to 65 Fahrenheit. Are you joking with me? That is just bonkers. 65 degrees Fahrenheit. Why do we care about ice? Why have I shown you so many things about ice? Because as ice melts, it raises sea level. Just to put this in perspective, if Greenland melted, we would have about 30 feet of sea level rise. And if Antarctica melted, West Antarctica melted, I think about 15 feet. I don't have the exact data, but it's on that order of magnitude. So the amount of water contained in ice shelves is huge, and in these ice sheets is huge. And we are on track to have approximately a meter of sea level rise by the year 2100. Now, is that bad? How bad is it? 150 million people live within a meter of sea level rise, or live within a meter of current sea level. So 150 million people will be displaced by the year 2100. In Bangladesh alone, 20 million people will be displaced. So what I'm showing you here now is a topological map showing elevation above sea level, and the left-hand image is Asia, and the right-hand image is a zoomed in focus on Bangladesh, and the colors tell you how far above sea level different land regions are. The dark red is the area that is most susceptible to sea level rise. So this is, imagine you're India, right? And you've got 20 million dislocated, generally impoverished climate refugees on your border in Bangladesh. What is that going to do to the social fabric in that area and national security issues? It's a thing that we've really got to start worrying about. All right. So I'm going to move a little bit toward some positiveness. What can we do about this problem? How can we move forward? There's no silver bullet. There's not one thing that we can do. There's no magic pixie dust, but there's silver buckshot. Now, what I'm showing you here is carbon emissions out to 2050 if we don't do anything. But if we do a bunch of things, add them together, it can make an impact. So these little changes that we're making in our society, they add up. You know, if you can come up with a technology that reduces emissions by 1%, and if 20 other people come up with similar technologies that reduce emissions 1%, that's going to be a significant decrease on emissions. So I don't want people to think that we have to have one solution that totally solves the problem. We have a bunch of things that we add together. Now, this graph, it's really, really busy, but I'm just going to focus on the key message. This is the levelized cost of energy. How much energy costs? And it goes back to 2009, but I want to focus your attention on some of these that are dropping dramatically. So wind is, I think, this gray guy right here. Wind has started out up here and it's now cost comparative with fossil fuels. We have solar, utility scale solar, and we've got solar thermal. So what we have seen, this is solar, this orange one that starts way up here. What we have seen is an incredible drop in cost of green energy supplies. And now, if you want green energy, you can get green energy at a lower cost than traditional coal power plants used to be. So you can save money and the environment at the same time. I'm just going to tell you a little bit about my own personal story. This is my car. I've got 2 electric cars. When gas goes up, I don't care. Gas could be $5 a gallon. Doesn't bother me at all. I drive totally electrically. Saves a lot of money. On my house, I have solar panels. Those solar panels feed right into my car charger. So not only does it run my house, but it also charges my car. So, and at the end of the month, especially in the summer, I get money back from Xcel Energy. I don't have to pay money out. The return on investment of these solar panels is approximately 7 years. And you don't have to have solar panels to drive an electric car. Driving an electric car, even if you're connected to the municipal grid, is still cheaper than buying gas to put it in your car. That's just another photograph. There's a little delay. There's a photograph of the panels on my garage. And there's a real trend. I mean, look, the world is changing. We are rapidly moving to electric vehicles. We're rapidly moving to green, sustainable energy sources. This is a graph that shows the huge increase in plug-in electric vehicles that are really reshaping the landscape of transportation. Change is possible. And this slide is a very uplifting slide for me because on the left-hand side, it's got a rusty oil well in the foreground with beautiful wind turbines in the background. And remember, those wind turbines are cheaper, producing cheaper energy than the oil well used to. On the right-hand side is an entrepreneur who's growing algae-based biofuel. So in those green polymer tubes, he's got algae that sucks carbon dioxide out of the atmosphere, and then he can put it into his vehicle and drive. Change is possible. We can make the world a better place if we work together and take action right now. So there is good news out there. The best news in my mind is the lower cost of green energy. I love to buy electrons from farmers in Minnesota or get solar power from the sun, employing solar installers in Minnesota. Much better to support the local economy in Minnesota and not have to send our sons and daughters to fight to keep oil routes open. So we can build the economy and save money and the environment all at the same time. And that's what gets scientists like me, that's what keeps us optimistic. And I think that's the end of my slideshow. So I'm going to do a stop share. Oh, what? Oh, wait, whoa, wait. I got more. Hold on. Okay. Um, let's see here. Okay. Yeah, I'm sorry. I went black and then I realized I had this slide. So I'm a scientist, but I'm also human. And sometimes people don't connect humans with scientists because we're sort of strange. But why am I giving a talk like this to the NPCA? It's because the science is interesting, but also our legacy is important. These are my daughters. This is Olivia, and this one on the screen is Lilith. Those are the first two daughters that my wife and I had, and they are growing up in a different planet, and we have had the fortune of experiencing the beautiful diversity that this planet has to offer. This is Olivia on a safari where we got to get up close to giraffes. I've also got another daughter on the screen now. She is adopted from Uganda, and she is now a full-fledged Minnesotan. She loves Minnesota outdoor activities. I'm showing a picture of her because well, first of all, she's great. This is, by the way, my fourth daughter, Neve, who's also adopted. But my daughter from Uganda is from a country that is already feeling the climate change in their daily lives, people's daily lives. It's a subsistence agricultural community, and they are less resilient to climate change than we are. I'm showing some pictures of the beautiful splendor of this planet. And so, whether it's your kids, whether it's the beauty of this world, we want to maintain this world for the next generation. And this is a photograph of myself and my family visiting a Maasai village. My kids are going to ask me one of two questions when they get older. They're either going to say, Dad, you knew what was going on, but what did you do about it? Or they're going to ask, Dad, you knew what was going on. How did your generation find the uncommon courage to take action to preserve this planet for us? I definitely desperately want my daughters to ask me that second question. And it's things like what I just showed you in this slide with the photographs that motivates me to come out and give talks like this, because change is possible and we can make the world a better place. I'm going to leave you with four notes, four things to remember, because I've covered a lot today. Item one, we know. Scientists have known for over 150 years, we've known about climate change and we've known about greenhouse gases. This isn't something new. It's not something that Al Gore invented. But we can solve the problem. We can solve it today with today's technology. We don't need cold fusion. We don't need alien technology. We can solve this problem today. If we're smart, not only can we solve the problem, but we can help the environment, create jobs, generate our own energy, and improve national security. There's so many co-benefits that you get from moving away from greenhouse gas polluting fuel sources. And the last thing I want to point out is there is a cost to delayed action. You know, some people say, John, it's just too expensive to take action on climate change. We've seen the cost, $600 billion last year. My response is, it's too expensive to do nothing. Doing nothing is a choice. And if we delay action, it's going to cost us more in the future. So those are the four takeaway messages that I wanted to leave you with. And then I'm going to try to do a stop screen share here. I got to figure out how to do that. And I think I'm back. So with that, I will be happy to take any questions that people may have.
Yeah, thank you so much, John. That was a wonderful talk. We don't have any questions in the chat right now, so if you do have questions, feel free to put them in the chat, or if you're brave, you can unmute.
Yeah, John, that was really,
if we don't
really
get questions, I'm going to ask questions of you guys.
So really compelling. You say, well, we're waiting for people to think of their questions and put them in the chat. Takes a minute or two. I do have a question for you to just kind of warm us up and get us going.
Yeah.
One of the things that I've been wondering is this: over the years, you know, we hear about climate scientists warning us about the changes, but I think as scientists generally, we're trained to be very conservative in our assessments and in our predictions, right? Everything has got to be P equals 0.05 or less, or 95% CI. And I'm kind of wondering what your take is when it comes to the climate. Do you see climate scientists as being like overly cautious, quote unquote, in making predictions? I mean, it seems to me that this is unfolding faster than anyone predicted even 15 years ago. And I'm kind of wondering what your take is on that.
Yeah, that's a great question. Scientists, and you are exactly right. Scientists tend to be conservative, and scientists focus on what we don't know. You know, you'll often hear scientists say, you know, John Abraham, do you think climate change caused this hurricane? And a scientist's typical first answer is, well, we can't definitively connect any weather event with climate change, but blah, blah, blah. And that's burying the lead. What scientists need to do is focus on what we do know. We know that changing climate is making more extreme weather, and it's making the weather effects more severe and more costly. And scientists aren't wired to talk like this. We are wired to focus on the uncertainty and the caveats, and that's been a big hurdle actually for communicating this issue effectively to the general public. Now, scientists are getting better at that. And in fact, I worked with an organization about a decade ago to train scientists on how to give interviews and how to provide information in clearly articulated ways that can connect with people. So scientists are getting better at it, but it is something we're not wired for. And so more work still has to be done. But you'll see that there is a number of scientists around the world, and I'll give you some examples. Mike Mann, you may have heard of, a scientist named Katharine Hayhoe is another one out of Texas. She's probably the best climate communicator. But I've got this beeping on my freaking computer, and I'm afraid that if I mute it, I'll mute you guys. So I apologize if that's coming through. But there are some scientists. Katharine Hayhoe is number one. She's the best. Mike Mann is great. You've probably heard of him. There's another guy from Australia, Kevin Trenberth, who's really good. So scientists are getting better at it, but it is something that we have not been good at, and we need to rapidly improve. And frankly, we should have been better advocates for the science for the last number of decades.
Carl, you have your hand raised. Do you want to unmute and ask a question?
Hey, John, thanks so much for joining us today. I also work on climate change issues every day, and I think now that we're all thoroughly mad and sad and shocked and depressed and filled with anxiety, I appreciate you giving us some idea of an outlet for that energy, which is everyone asking what they can do and how they can explain to the next generation what they tried to do. I'm curious, my question for you is, do you see any role of or need for serious research on things like geoengineering? And are we relying too heavily on the hope for carbon capture and storage?
Boy, that's a good question. So how do we solve this problem? There's two things we have to do. We have to mitigate. Adapt means we have to make our society more resilient to climate change. So that is making our cities more resistant to flooding, making our coastal cities, especially in the Southeast, more resistant to high winds, making our agricultural industry more resistant to drought, flooding. We have to make our society more resistant to reduce costs when climate disasters happen. Now, there's a limit to how much that can be done. I mean, let's talk about Miami. Parts of Miami are experiencing flooding in high tides now. And it's going to get worse. And you can't build a wall around Miami because the porous substrate allows water to percolate up from the ground. So while we can adapt in some circumstances, other circumstances, adaptation is very problematic or impossible. The other thing that we need to do is mitigate, and that means reduce the effects of climate change. Now, climate change is here, it's happening, it's going to get worse regardless of what humans do. We have what's called warming in the pipeline. That is, if we don't do anything, Or actually, if we cut emissions to zero right now, we would still have some warming that will happen because of past emissions. But we can take a trajectory that's like this and make it like that. That's the goal. Is to make the impacts less severe and to give us longer time to adapt. Now, how do we mitigate? We need to reduce carbon dioxide in the atmosphere and other greenhouse gases. And probably the second most important one that I discussed was methane, which is from our agricultural societies, industries. So we have to reduce emissions of greenhouse gases. And to the extent we can't, and by the way, carbon capture and storage is in that vein. It's removing carbon dioxide from polluting sources and then using that carbon dioxide somewhere else. And I've actually been involved in a CO2 pipeline hearings and legislation and rules and regulations for that. There are some costs and concerns about carbon capture and storage. And definitely there are risk factors. It's a double-edged sword. I mean, I love to see carbon dioxide come out of the atmosphere. And I love to see that CO2 used for something useful. But it has to be done in a way that is safe and in a way that doesn't give free rein to polluters to just keep polluting. Now, let's say we can't adapt and mitigate our way out of this. Then our last option is geoengineering. And geoengineering is essentially a way to use the earth to reduce its own carbon dioxide. I'll give you an example. One geoengineering option is to seed the oceans with iron powder. Why is that? Because if you put iron in the oceans, it causes an incredible algae bloom. And when the algae grows, it pulls carbon dioxide out of the atmosphere. And then when the algae dies, it sinks to the bottom of the ocean and it sequesters that carbon dioxide. That's an option. That is a type of geoengineering. Another type of geoengineering is to simulate volcanoes. Some volcanoes, when they erupt, put little particulates up in the atmosphere that block sunlight and they cool the planet for about 2 to 3 years. If we could make synthetic volcanoes, that would help cool the planet. So those are just two geoengineering options. I'm really skeptical. I mean, they might work, but I am really skeptical about injecting pollutants into the environment so that we can get rid of a pollutant. I mean, there are a lot of unintended consequences for that. And you've got to keep, if you start making artificial volcanoes, you got to keep doing it because the effect only lasts a couple of years. So you're committing yourself to long-term geoengineering, and we really don't know what the negative consequences are. So geoengineering is an option. Scientists are taking it seriously, but it is definitely a last-ditch approach in my mind. We would do much better by just using our energy efficiently and maximizing green energy production. I mean, think about fossil fuel. Think about a gallon of gas. A gallon of gas is magic. It has so much energy. It will take an SUV, push that SUV 60 miles an hour for 20 miles. Think of how many cheeseburgers you'd have to eat to have that kind of energy. Gasoline and fossil fuels are super energy dense. They are magic resources. We should use them wisely. We shouldn't waste those kind of resources. So in my mind, the first thing that we want to do is just use energy more efficiently. And I think we could cut our emissions by about 30% just there. And then step two is to maximize clean and renewable energy, especially wind and solar and hydro. And then step three would be to look at geoengineering, but it would be a last step in my mind. Sorry for the long-winded answer.
No, that was a great answer, John, and it actually answered one of the other questions. We are at 10:01, so I don't want to keep anybody, past the top of the hour. There are a couple more questions if you want to try and answer them, or if you
let's
that
take
people
a
can
few
reach
minutes.
out to. Okay.
People can reach out to me. I didn't put my email. Look, if you Google John Abraham, University of St. Thomas, you'll find me. I don't know if you guys can distribute my email address. That's totally fine. I am very findable.
Or if you want to type it in the chat.
Yeah,
See that too?
actually, that is so smart. If I can find the chat. Oh, there it is. Okay, I will type it in. I've got a window that's sitting over my chat. Okay, let's see. Here we go. Okay, it's in the chat. Do you want me to just answer these questions on the left?
Yeah, for sure. The first one was about geoengineering, so I think
Uh,
we touched on that.
yeah, and then
But yeah, we've
we've
got
got this
John's question and Deanna.
Yeah, well, so this low sulfur, that's not quite geoengineering. There's a, let me just really briefly say the ocean temperatures over the last 14 months are off the chart, and scientists, we don't quite know why. We think it's long-term warming that has just gotten a little extra worse, but there is a vigorous debate right now about why the oceans have just did a step change about 14 months ago. One one concept is that it's low sulfur fuel in ships that is increased the rate of warming, and that might be true, but the patterns of warming that we're seeing don't comport with that concept. So Benton has a good question here. It's an area of ongoing research. Changes to ocean ship fuel could be a factor, but it's really not settled, and scientists are looking at that right now. John G asked, the price of energy should be a driver. How do we break the stranglehold of politics? John, I got to tell you, I've been working at communicating this issue for 20 years. And the best way to break the stranglehold of politics is to point out that you can save money and the environment at the same time. I mean, in the olden days, people who were on the right side of the political spectrum would talk about the cost of green energy. And now that's not an argument, because green energy is now, look, we can generate jobs and save the environment and save energy at the same time. So if you want to appeal to people who are on the right-hand side of the political spectrum in the US, I think the way to do it is through prices and jobs and economic opportunity. And I'll tell you this, I work around the world. China is eating our lunch in green energy. I mean, the future economy is AI, water, energy. And the US is getting totally boxed out in green energy around the world. I would rather us export our solar panels around the world and not have to buy solar panels from other people. So it's an economic opportunity, and that would appeal to people on both sides of the aisle. And the last question is deforestation. How big of a role? Deforestation, it's a good question. My recollection is it's significant, like 20%, maybe 15%. Deforestation, when you deforest, when you cut forest down to create farmland, then those forests are burned. Not only do you burn the forest and release carbon dioxide in the atmosphere, but you reduce the ability of that forest to sequester carbon into the future. It's a major factor. I think it's around 20%, but I don't have the exact numbers. And clearly, I talked about silver buckshot. A lot of things that you have to do added together make the impact that you need. And dealing with deforestation or reforestation is one of those buckshot pieces, critically important.
Awesome. Well, I think those are all our questions for today. Thank you so much for giving such an interesting and a humbling talk, I would say, today. But I'm glad we left off on a positive note. So
well, and the MPCA does great work, so keep it up. You guys are part of the solution. And anyone can reach out to me if they've got questions.
awesome. Thank you so much for your time today. We really appreciate it.
Bye, guys.
Yeah, thanks, John. It was great.